Have you ever woken up in the middle of the night in a panic, wondering how to extract a polygonal mesh of an isosurface from a three-dimensional discrete scalar field? Yeah, I didn't think so. But back in '87, two programmers at General Electric did. They created and patented the marching cubes algorithm, an algorithm that has likely saved countless lives by allowing doctors to visualize data from CT and MRI scans. Whenever you instruct a machine to solve a problem with code, you're creating an algorithm, a procedure for rearranging ones and zeros that can make animals talk and vacuums walk. Most algorithms belong in the dumpster, but some are fast, some are beautiful, and some are so weird they're indistinguishable from magic. Today we'll look at 10 of the most interesting algorithms ever engineered, and how they're used to solve very interesting problems in the real world. First on the list, we have wave function collapse. One of the weirdest things in all of science is the double slit experiment, where particles behave like a wave when you're not looking, but when you look, they suddenly collapse down to a particle. It seems counterintuitive, but it makes total sense when you realize we're living in a simulation, and the universe wrote this algorithm to cut down on its AWS bill. It's an interesting concept to think about philosophically, but the general idea behind wave function collapse can also be implemented programmatically. Imagine we have a map for a video game, but what if this is a side-scrolling game that can go on for eternity? We can't just make a bigger map, we need an algorithm to procedurally generate it on the fly. What's so weird is that we can take this initial map and think of it as being in the initial superposition of all possibilities. It's the wave function. Then upon observation, it collapses into a particle, or in other words, it selects a random map tile, but follows a consistent set of rules, like in this case, making sure that the roads are always connected, providing a random yet cohesive result, and doesn't rely on any sort of modern generative AI. Speaking of which, AI is weird as hell. Diffusion is a machine learning algorithm originally developed at OpenAI and is the magic behind image generators like DALL-E and Stable Diffusion. But the concept of diffusion actually comes from thermodynamics, where particles spread from areas of higher concentration to lower concentration. In artificial intelligence, the process is reversed. The algorithm starts by generating random noise, which would be like high entropy in thermodynamics, and gradually refines it to a structured image, which would be lower entropy. But first, you'll need to train a model that can do this well. The diffusion algorithm works in two phases. In the forward phase, it gradually adds noise to an image step by step until it becomes completely random. In the second phase, the algorithm reverses this process, reconstructing it back into a coherent image. When the algorithm runs over millions of labeled images, we get a collection of weights that can be used to generate new images out of thin air, allowing us to build an infinite army of OnlyFans models. It's highly compute intensive, but also works well on audio, and the next frontier is diffusion for video generation. But now let's talk about simulated annealing. One frustrating thing about programming is that for many problems, there's not just one solution, but many solutions. Like an Amazon warehouse has many different ways to organize its inventory, but some ways are more efficient than others. Annealing is a word that comes from metallurgy, where metals are heated up and cooled down over and over again to remove defects. The same idea is used in optimization algorithms to find the best answer in a sea of good answers. Imagine trying to find the highest point in a mountain range full of peaks and valleys. A simple hill climb algorithm won't work because there are many local peaks. Initially, the temperature starts high, allowing the algorithm to explore freely. As time goes on though, the temperature is lowered, which decreases the probability of accepting a worse solution. The trade-off here is exploration versus exploitation. But the reason I included this algorithm is because it's also a good way for beginners to learn how to code. Initially, you start out exploring all kinds of different technologies and frameworks, then eventually you find one specific area to exploit and specialize in. But we can't talk about algorithms without talking about sorting, and the most ingenious sorting algorithm of all time is without a doubt sleep sort. The majority of sane sorting algorithms out there use strategies like divide and conquer to break up an array into subarrays where it can be sorted more efficiently. However, some random genius on 4chan found a better way, but it's a bit unconventional. Here's what the code looks like in Bash. It's incredibly simple. It loops over the array, and then for each element, it opens up a new thread that sleeps for the amount of time proportional to the value of its element. Then finally, after waking up, it prints that element. It's genius because it delegates the sorting to the CPU's scheduler. It's also incredibly dumb and useless because it delegates sorting to the CPU's scheduler. Speaking of which, you might be familiar with another useless sorting algorithm, BOGO sort, which tries to sort an array by randomly guessing over and over again. It's like playing the lottery. But what if we apply the same algorithm with quantum mechanics to the multiverse? If we're to trust multiverse science, we know that all possible outcomes exist in separate parallel universes. That means as a developer, if you find yourself with an unsorted array, there's some other parallel universe where it is sorted. The technology isn't quite there yet, but if we could randomly observe these other universes to find the sorted array, we could then use a portal gun to travel to that universe, which would make our lives much easier. Although we would obviously have to kill the version of ourselves in that universe, but if it's a really large array, quantum BOGO sort might be worth worth it. That's purely hypothetical, but one of the most practical and goated algorithms of all time is RSA, a public key crypto system. It's essential for digital security, allowing people on the internet to lock their mailboxes and sign their letters with a unique signature. But it's based on one simple mathematical reality. Multiplying large numbers to find two original large prime numbers is extremely difficult and time-consuming, like it'd take your laptop 300 trillion years to brute force. Unless quantum computers become a thing, and we can start leveraging Shor's algorithm, which can solve the integer factorization problem exponentially faster than any classical algorithm. Prime factoring is pretty simple, but how this algorithm does it is where things get weird. It relies on concepts like qubits, superposition, and entanglement to perform massive amounts of calculations in parallel. The algorithm is legit, but so far, the biggest number ever factored is 21. Even IBM's state-of-the-art Q System 1 fails when trying to factor the number 35. However, just recently the Chinese factored this big-ass number with a quantum computer, but it uses a different algorithm that doesn't scale very well for large numbers, unlike Shor's algorithm. Everything is safe for now, but when someone figures out how to make quantum computers work, expect all hell to break loose in the cybersecurity world. At the beginning of this video, I mentioned the marching cubes algorithm, but it deserves a closer look. So first, we start with a 3D scalar field, which might represent data from an MRI machine. Each point in the 3D space is represented by a single number or scalar. The algorithm starts with a single point, then takes its 8 neighboring locations to form an imaginary cube, but treats the 8 values as a bit in an 8-bit integer. This results in 256 different possibilities, which point to a pre-calculated array of polygons. The algorithm marches through each point to create a 3D mesh that can be used in 3D software. And at the time, this was really cool because MRI machines produce slices of data that can now be rendered in 3D. In modern times, though, we're often dealing with distributed systems in the cloud. And that brings us to the Byzantine generals problem. Imagine you're a general in the Byzantine army. You're camped around a city with a few other generals with plans to attack it the next morning. But what if one of the generals gets drunk and wakes up too hungover to attack? The entire system could collapse. Computers have the same problem. Sometimes they might fail or be infiltrated by hackers, and you never know when or where that's going to happen. Luckily, algorithms like PBFT are designed to solve this. They can keep a distributed network working properly, even if up to 1/3 of its nodes go haywire. It works by having a node broadcast a pre-prepared message to other nodes, indicating its readiness to execute some code that will change the system. The other nodes will respond back in agreement, then after a certain threshold, a consensus is formed. Once there's a consensus, the original node sends back a commit message to all the other nodes, which can then all execute the changes, making the entire state of the system consistent. Algorithms like this are essential for blockchain technology and things like distributed cloud databases. What's really cool about algorithms, though, is that they can also reflect nature, like Boyd's artificial life program. It was created back in '86 and simulates the flocking behavior of birds. What's so cool about it is that it demonstrates the emergent complexity or beauty that we get out of just a few simple rules. In this case, the birdoids have 3 rules. They steer to avoid crowding, they steer towards the average heading of the flock, and they steer towards the center of mass of their local flock mates. The end result are these intricate patterns that weren't programmed directly, but just emerge naturally. But finally, that brings us to an old algorithm that blew my mind just the other day and inspired this video. Boyer-Moore string search. It's weird because it becomes faster and more efficient as the string it's searching becomes bigger. That seems impossible, but it makes sense when you understand the algorithm. It scans text from right to left, then has 2 rules. When it encounters a bad character not found in the search pattern, it jumps past it based on an estimation made in a pre-processed table. Likewise, if it finds a partial match, then a mismatch occurs. It has a separate pre-calculated table that maximizes the number of characters it can safely skip. These rules are called heuristics, which are like functions that are not guaranteed to be perfect, but are far more practical than looping over every single character. In this case, the algorithm gets faster with more text because it's able to skip a higher proportion of characters. And if you've ever wondered why grep is so fast, you have this algorithm to thank.